Okay, so we're going to continue with part two of the incline forces review here. So here's the problem. We just have a couple graphics here. We have a 4 kilogram cart released from the top of a 2 meter long incline. So this whole incline here is 2 meters long. The cart is 4 kilograms, and we're going to neglect friction from the wheels, and we're going to neglect drag as well. All right, so let's start with what is the magnitude of the net force on the cart? So we're looking for this. All right, so we can start by drawing force vectors. We can draw a free body diagram. Okay, so here we have gravity pulling down again, and we have the normal force working up from the track. All right, and really those are the only two forces happening, but we can break these down. We have the x component of gravity. That's going to be, the y component of gravity. That'll be cosine. And then we have the x component of gravity pulling us down the ramp. And that is going to be sine. Okay? So remember, net force is in the direction of movement. The only thing working down the ramp is going to be the x component of gravity. So that would be net force is equal to FGX, which is equal to mg sine theta. Okay, so remember where this comes from. So it's going to be gravity, so that's just mg, and then this is like my hypotenuse of my triangle. So if I want this little leg, which is also down here, I would have that angle, which is 15 degrees. Okay, so I can draw that triangle for you, kind of blown up a little bit. So that's y, that's x. Okay, so just so we remember from the last session here, and that is going to be, not that angle. This angle is going to be 15 degrees, and then my hypotenuse is the force of gravity, which is just mg. So if I want this, then I'm going to be using sine, and it would be mg sine 15 to get that. Okay? So it's going to be mg. So it's going to be mg sine of 15 to get FGX, or my x component of gravity. Okay? So let's plug our values in here. Mass of the cart, 4 kilograms. Gravity, 9.81 meters per second squared. And then we have sine of 15 degrees. All right, so put that in your calculator, see what you get. So we get 10.16, and that would be newtons. Okay, so my net force is going to be 10.16 because that is what is pulling us down the ramp. Okay, so 10.16 newtons is going to be pulling us down the ramp. So the next piece here, B, what's the magnitude of the cart's acceleration? So we have to remember what net force is going to be, or what force in general is going to be. Newton's second law tells us that force is mass times acceleration. Okay, so if we have the net force, we know 10.16, so that goes in for the force. Okay, so we have 10.16 newtons is equal to my mass, which is 4.0 kilograms, times my acceleration. And now we can just use our information that we have to find our acceleration. So we do 10.16 divided by 4, and you get 2.54. So we have an acceleration of 2.54 meters per second squared. Okay, so C, how long does it take the cart to get to the end of the ramp? So now we're going to have to use our kinematic equations, and we're going to have to remember that our ramp is 2 meters long from beginning to end. Okay, so our cart is going to travel 2 meters through the length of the ramp there. Okay, so you could look up your list of kinematic equations, okay, or you can have a few of them memorized. All right, so equation that we want to use is, since we have a distance, we have delta x equals initial velocity times time plus 1/2 acceleration times time squared. This is the equation that we want to use. because we have a distance, we don't know a time, and we do have an initial velocity. It's kind of implied here. Your cart is starting at the top of the ramp, so it'll start from rest. We have an acceleration that we just found right there, and then we can solve for time. So let's write our knowns. So delta x, that's 2.0 meters. Time, we don't know. Initial velocity, that's going to be 0 meters per second. And our acceleration, we just have right up there above, 2.54 meters per second squared. So we can plug this information into this kinematic equation and solve for time. So 2.0 meters there. Since 0 meters per second is my initial velocity, that is going to be gone. And then we'll just have 1/2 times 2.54 meters per second squared for that acceleration times time squared. Okay, so we can break this down. So 2 meters still, we take half of that, so it's going to be 1.27 meters per second squared. And then we have time squared. And then we're going to divide both by 1.27. And then we will get that time we're looking for. So do 2 divided by 1.27. And we get a time, or we get time squared, excuse me, t squared equals 1.57, and that'll end up being seconds squared, just for labels, and then we have to square root both sides. And we get a time of 1.25 seconds. So it takes us 1.25 seconds to get down the ramp. Okay, so that's C. So D here, what is the cart's maximum speed? So we want to find that speed right before it hits the bottom of the ramp. All right, so we can use our basic acceleration equation for that. It's also considered a kinematic equation. Acceleration equals change of velocity over time. All right, and then we have enough information to plug this in because this, remember, is final minus initial. And we can just plug everything in. So 2.54, I'm not going to worry about labels here, we're just going to plug it in. Final velocity will be there because remember the initial velocity is 0, and we have a time of 1.25 seconds. So we get our final velocity. You'll end up multiplying both sides by 1.25, and we get 3.19. So 3.19 meters per second. That is the final velocity at the bottom of the ramp. Okay? So that is how we use our force equations, all right? So our inclined forces and our kinematic equations. So in order for us to use like our kinematic equations, we have to have some kind of like a time or a distance involved, and we're looking for how fast the cart is going after how many seconds or so many seconds that it went down the ramp. Okay? So let's look at the next one. So now we have another force involved, which is tension. Okay, so tension comes from like strings or chains or some like cable or something like that. So there's going to be tension on this cable that's going around the pulley. Okay, we have mass 1 being 10 kilograms, and mass 2 we don't know. They're linked by a string. The system is at rest. That's important information. We're going to neglect friction, drag, and the mass of the cable. And you forget about mass of the pulley as well. So we're just basically looking at the masses of the two weights here. So with problems like this, we can draw a couple free body diagrams, or we can draw force vectors on each of these. I'm just going to draw force vectors on this one here. So let's make that blue. So we have, so we have gravity pulling down, and we have, I'm just going to draw it up here, normal force working up. And now we have a third force, is tension. Okay, so tension is what's holding that from going down. All right, so then over here we have a gravity force pulling us down. We have a weight, and then we have a tension force. Okay, so tension. So the nice thing here is that we have this string and these two things are connected. Okay, so that means the tension on this one, if we forget about the drag and all that stuff here, is going to equal the tension on that one. So these two are going to be equal. So those tension forces are going to be equal. Well, we know the system's at rest, so that means this is not moving up or down. So this one is in equilibrium with that. So all three of the forces that I circled are going to be equal. So if we find this, we'll have that, and we'll have that, and then we can start to work with these two over here. Okay, so let's start that and let's figure it out. So for A, how much tension is on the string? Well, the force of gravity for, I guess we could do another subscript, mass 2, is equal to the force of tension on the string. And so force of gravity on mass 2, we don't know, so that's what we're going to be looking to find. Okay, so maybe we're going to have to be working the other direction because we don't know mass 2. So we're going to have to start with mass 1 here. All right, so I started at it from the wrong direction because we didn't know mass 2, so we're going to have to start here and work our way that way. Okay, so for A, let's break this down into components. Okay, so we have our Y component here, and then we're going to have our X component there. And what is actually going to be balanced with that force of tension here? That's going to be our X component. So either way, if we look at it starting from here or here, we're going to have some things that are balanced with tension. Okay, so the net force on this is going to be 0. And that's because we have the X component of gravity balancing out tension. Okay, so if we wanted to start with a net force equation, we could do that. F net is 0, and we could write it's going to be force of gravity minus force of tension, which is going to be 0. So force of gravity is equal to, write that 0 there because we're balanced. Force of gravity is going to be equal to force of tension. So we have to figure out this, and that'll give us tension, and then we can kind of keep rolling from there. Okay, so remember gravity on that block, so that's mass 1 times g times sine theta, and let's plug our values in. So we have 10 kilograms times 9.81 meters per second squared times sine, and our angle here is 30 degrees. Okay, so let's plug that in our calculator and see what we get. So we get a gravitational force of 49 newtons working down the ramp. Okay, that's our X component of gravity. So from there, it's just going to kind of be like a domino effect because we're going to go from one thing to the next. So how much tension is on the string? Well, if this is 49 newtons pulling me down, then tension is 49 newtons holding us up. So force of tension is going to be 49 newtons holding us back up. Okay, so let's do B here. What is the normal force on M1? Okay, so how do we find normal force again? Well, normal force is equal to the gravitational component in the y direction. Okay, so normal force equals FGY. And to get FGY, remember from our last problems, that's going to be cosine. So we will have mg, we can write 1 there if we want to, mg cosine theta. And let's plug our values in. So M1 is 10 kilograms, and G is 9.81 meters per second squared, and we have cosine of 30 degrees. Okay, so let's put that in our calculator and see what we get. So for this one, we get 84.96 newtons. So that is the y component of gravity. That is also our normal force. Okay. All right, now to answer part C. So we kind of started going with that here. So if I found the gravitational component in the x direction, all right, that's what's pulling me down the ramp, right? Then that's going to be equal to tension, all right? So we had that equal there earlier, F tension, that's 49 newtons. So that tension is equal to that tension, because it's the same string, it's connected, okay, just pulling a different direction. And then this tension is equal to the force of gravity for mass 2, because it's not moving up or down, okay? So we could say force of gravity for M2, which is the weight, is 49 newtons. So M2, the weight for M2 is just 49 newtons. So the last part, we're going to use that weight, right? So if we got force of gravity, that's 49 newtons. What is the mass? So Fg is mg, and since we're on mass 2, I'll write m2. So what are we going to do here? Just to find m2, we're going to have to divide out gravity. Okay, and gravity is 9.8. So I'll write 9.81 meters per second squared. We're going to divide out gravity, see what we get for mass 2. And we get 4.994, let's just call it 5 kilograms. Okay, so block 1, or mass 1 here, was 10 kilograms. Mass 2, we worked all the way through this, and we found out that it was 5 kilograms. So this is a balanced system if we disregard friction and whatnot. Okay, so the takeaway here is if we have the pulley system with a string or a cable, that tension is going to be the same. Okay, and that works with things that are moving or not moving here. That tension here is connected to the tension here. Okay, let's look at one more problem, and then we'll call it good. So last inclined plane problem, we're kind of looking at a system that's in equilibrium again. So a UPS driver is pushing a box up the ramp at an incline of 12 degrees. The driver exerts a force of 350 newtons up the ramp to prevent the box from sliding. What is the weight of the box if we disregard friction from the ramp? Okay, so now we have, let's draw some forces here. So gravity on the box and normal force on the box, and now we have an applied force pushing on the box that way. So the box is not moving, okay? We're just preventing the box from sliding down the ramp, and we're trying to figure out the weight of the box. So we know that we're pushing on the box at 350 newtons. All right, and it's not going anywhere. So what should that be equal to? Well, if we think about our components here again, so we got the x component there, y component there. All right, well, the applied force is going to be equal to that x component of gravity, right? Because it's not going anywhere. So we can set this equal to FGX, and then we know from the last few problems that we've done what's FGX. So we're going to have 350 newtons equal to mass times gravity times sine theta. Well, we have enough information here to figure out the mass of the box, okay? Or we have enough information to figure out the weight of the box, right? So weight is going to be that mg part. So what do I need to get rid of to just get mg? I'm going to divide out sine theta, okay? And we know that theta in this example is 12 degrees. So mg, or let's call it weight of the box, is going to be 350 newtons divided by sine of 12 degrees. And we get the weight of the box to be, it's quite a large number here, so 1,683.41 newtons. Okay, so that is the weight of the box. And if we wanted to go further down, maybe we want to figure out the mass of the box. If you divide that by 9.81, then you can get the mass of the box, which is 171 kilograms if we wanted that. 0.6 kilograms. Okay, so if we divide by 9.81, that's what gets us the mass of the box. Okay, either one, but in this question it asks us to do the weight. Sometimes you'll have questions that ask you to find the mass, so that's just taking it one more step and dividing by 9.81. Okay, so these are a handful of inclined plane problems, quite a few different scenarios, so hopefully it helped you review a little bit, and let me know if you have any questions. Thanks.